Okay. Well, today we've got Rachel St.Clair, who has a PhD in complex systems and brain sciences, postdoc at working on philosophy of conscious machines in AGI, and the founder CEO of Simuli. So that's quite a bit. Glad to have her.
Thanks, Mike.
Welcome.
So yeah, so thanks everyone for making time out of your Sunday or Monday, depending on where you are. Yeah, so I'm in the middle of writing this paper. We just submitted it to Frontiers. So once that's available, if you're interested, it should be published in the next couple of months, hopefully. But essentially, what I want to talk about today is kind of going through this new framework for learning that's an update to traditional AI. And so what I'm really after in terms of early AGI success is learning novelty efficiently. So this is one thing that traditional AI really struggles to do, is to learn things efficiently. And we'll kind of talk about that. So throughout kind of this whole talk that I'm going to be kind of discussion that we're having today, what I'm really after here is efficiently learning new things and then retaining that knowledge after learning them. So keep that in mind, that everything in this talk is centered around that goal. There are other goals that are necessary for AGI, of course, but I see this as kind of a first step or stepping stone towards smarter artificial intelligence that's more efficient. And the reason for that is because if you look at the human brain or any biological brain, we tend to learn within resource constraints. So that means that we have some finite number of neurons or learning units, and we're able to learn new things without forgetting old things. And we don't just grow a new neuron every time we need to learn something new, which is essentially what deep learning is doing. And this is in part because in brains, we have synaptic connections that change to support this adaptive learnability. And one of the cool things that you get out of being able to learn within resource constraints is that you have an ability to recover after damage, which is pretty cool, because that means that the information must be multiplexed or kind of spread around and not stored in like a content addressable lookup fashion. And we're constantly learning things and learning to adapt to novelty on the fly. So you might be thinking, like, why is novelty so important? And if you think about the way that biological organisms learn, is that no two instances are ever the same, right? The way the photons hit your retina is never exactly quite the same from moment to moment. So we are constantly learning novelty. It is extremely hard, if not impossible, to get two of the exact same instances. And of course, they're structured to the natural world, and we want to capitalize on that structure in the natural world. But every instance is new. And when we learn those new things, we want to be able to not forget them when something new comes along, right? So if you learn how to ride a bike and then you learn how to drive a car, you don't forget how to ride a bike. And if we look at AI, so traditional AI, you can kind of fill in almost any modern popular AI system here. But specifically deep learning is that it learns without resource constraints. And you might be thinking, well, resource constraints, that sounds like a bad thing. Why do I want to learn within resource constraints? And that's kind of what my whole spiel is here, is trying to convince people of, is that being able to learn within resource constraints means that you're learning correctly, that you're able to learn and generalize and distribute that information across whatever learning system in a way that actually gives you benefits that are useful and productive for learning. And so when we look at AI or deep learning, we see that kind of what happens is we end up adding more neurons or nodes. I don't know if we can quite call them neurons, but we add more information learning units in order to increase the learning capacity. And that most of the time, for almost any system, these connections between the nodes are static. Once they're learned, the system is shut off and it's put into inference mode, and there's no continual learning or lifelong learning. So if you look in deep learning or AI literature, there is a large subfield that's focused on lifelong learning or continual learning, but there hasn't been much success in that area. And that's in part because all of these AI systems learn without resource constraints, which means you have to keep shoving in more computational power every time you want to learn something. It's very antithetical to the way that biological organisms learn. This also means that your significant damage threshold is lower. So if you were to take a neural network and then kind of just like zap out half of the nodes, the ability for that system to make up for that learning is significantly damaged, in the sense that there is a number of computational units needed to learn some task. And in the brain, it's much more adaptable, and that you can do without an exact number of neurons and still recover partial, or even a lot of times fully, the entire task of learning. The other issue with AI here is that we don't really train our AI systems on novelty. So typically in a deep learning system, you'll have a collection of data, your training data set, and you'll iterate over that training data set hundreds of thousands, sometimes millions of times. So you're almost memorizing, right? Like you have these it's almost like flashcard learning, where you like give flashcards to a deep learning system, and then you continuously do that until it is kind of memorized that stuff. And it happens to memorize it in such a way that it can sometimes during testing tell you what that testing task is going to be based on the training task. This is much different than the way the human brain learns, where everything is novelty and there is structure that is repeated and capitalized on, but no two things are ever the same. And the biggest problem, which I've been harping on for a while here, and I will continue to do so throughout this talk, is catastrophic forgetting. So in deep learning systems, there's a problem known as catastrophic forgetting. Most people have widely ignored this problem. That's because we just make models bigger and then they do better. So we're solving this problem with what I would say is a band-aid approach. You just make the model bigger and then it can learn more, which again is not how the brain works. But ideally, the work on catastrophic forgetting has tried to make some solutions, and basically those solutions can kind of be thought of, if we want to put like a blanket statement over all of the papers that have claimed to solve catastrophic forgetting, is a method of dynamically updating the weights. So most of the time they'll slow down the weight update function, or they'll freeze certain weights and not update them till later. These are all good approaches and it's good work, but we're not actually solving the problem. And I would like to argue, and I argue in this paper here that's coming out, is that backpropagation, the main learning algorithm of deep learning, is responsible for catastrophic forgetting. And so if you're using backpropagation to learn features, you will never be able to solve the problem of catastrophic forgetting, because it is built into the fundamentals of how that algorithm works. It degrades prior learning. So when you learn, if you're not familiar with like deep learning and catastrophic forgetting, what's happening is you have a collection of nodes or neuron-like things. You learn a task, and then as soon as that task changes even a little bit, like the next set of batch inputs from the training data, you'll automatically rewrite the entire network for the sake of the current task. So you're constantly moving your learning forwards towards the next thing. And by doing so, you're moving away from things you've previously learned, and you're degrading that prior learning. So this is causing problems. So if we look at deep learning specifically, and we look at this graph, what we're looking at is that the training compute time, so petaflops per day needed to train these systems. So one takeaway from this kind of graph is that it's getting faster to train these neural networks because we're able to compute more petaflops per day. Another way to look at this graph, the same information in here, is that we need more petaflops to train these models. And we need more petaflops on like an exponential scale. So since about 2010, we've been 10xing the amount of memory needed to learn these very large neural network systems. And I think that's a problem because we're headed towards two major compute walls. So the first major compute wall here is just a general computing statement, is that we know Moore's law is slowing down and coming to an end. And eventually we will not be able to miniaturize transistors, right? We'll get down to the size of atoms and we'll have these weird physical interactions. And just based on a back of the envelope calculation, we have at max 9 years. And I would suspect that it's much, much less than that before we can no longer miniaturize transistors any smaller. You can do that calculation on your own. Basically, we're at about 2 nanometers in transistor size. Pick any one of your favorite protons, the size of that proton. And if we're 2.5xing or diminishing the size of transistors every year, you can count out how quickly we will get down to the size of individual atoms and start encountering physical problems. There's other solutions for this, right? This is why everyone's scrambling for quantum computing, DNA computing, microfluidics. There's a ton of other computing options, analog computing, things like that. But this idea that we're going to just be able to make better computer systems to handle the AI workload is not going to last forever. So if we're not seeing the gains we want in traditional AI, we better figure it out soon, because just making them bigger is not going to be feasible here in the next several years, right? So just thinking that, oh, if we just make deep learning big enough, we just make bigger models, that we will get more learning, that idea is not going to hold up based on the hardware and the trajectory of hardware that we're moving into in the next like 9 or so years. So if we look at this graph, this is not Moore's law, this is what we call Kumi's law. So Kumi's law is saying that our energy efficiency is getting worse. So we were on a linear trend of energy efficiency until about 2000. And then in 2000 and 2009, we saw this really taper off. And so we're starting to hit some sort of logarithmic curve for energy efficiency in terms of what we're able to compute. And so the way this graph is kind of the way this statistic is measured, and you can go to this link down here if anyone's curious, or just look up Kumi's law. Basically what's happening is that you take the maximum compute load, the maximum amount of operations in the system, over the amount of watts that are being spent by that system. And so it's getting much less efficient, which is a problem. And so the reason we're concerned about energy here is because it has a direct translation to cost. And these AI systems are extremely expensive to train. So if you look at GPT-3, which is very popular, very well-known algorithm or model, language model, GPT-3, it costs about $4.5 million to train, which is not feasible for most people, especially not individual entities and most small businesses. And there's another study that shows that just one training run of a large language model can generate 626,000 pounds of CO2 emissions, which I think is equivalent in this paper. I think it's equivalent to like 4 lifetimes of a car from one model. So not only are these things, you know, very expensive in terms of financial costs, but they're also expensive in terms of energy cost. And so if we want these AI models to be all over the place and to scale them up to human level capacity, we don't want them to be sucking all of our energy out, right? So there's a lot of motivation for why you want efficient AI systems. And the second kind of big wall that we haven't been able to break through. So we're headed towards this compute efficiency wall. And there's this second wall, which we've been kind of butting up against for a while now, is that AI learning and bio-learning are not showing the same learning trajectories. So if you look at learning trajectories of biological beings and you look at learning trajectories of artificial intelligence, those things are not matching up. And so what I've done here is kind of compare Alex the Gray Parrot and GPT-3. And my reason for doing this is because the human brain has 86 billion neurons. And if you want to estimate the number of synapses, pure estimate here, it's around 1 trillion, right? And so what we're looking at is, even if you think that nodes in a neural network are more like synapses and less like neurons, then we already have models with more synapses than we think the human brain has. So if we look at Wu Dao 2.0, which is a Chinese language model, it has 1.75 trillion nodes. And if we look at Google Switch Transformer, that's 1.6 trillion nodes. So I don't think that argument really holds up if you say, okay, well, there's just more actual computational power in the brain. I think that's not what we're seeing, right? What we're seeing is there's less computational power in the brain, yet we have more generalizability. And so if we look at Alex the Gray Parrot, he only has 1.6 billion neurons compared to GPT-3, which has 175 billion learnable parameters or nodes. And Alex the Gray Parrot can do lots of things, right? So Alex the Gray Parrot can identify materials from touching it with his beak. He can understand basic English. He can fly. He can decide what to eat and then eat that stuff and be fine. He can do some basic counting and arithmetic. He can identify shapes, colors. He has color, spatial, and temporal invariance. He can understand some causal relationships and express emotions as far as humans are able to tell that another animal can express emotions. And he has some basic common sense. So GPT-3 can do some even more amazing things than Alex the Gray Parrot. So GPT-3 is capable of advanced language, including coding. It can also program in various programming languages. It can do language translation. It has the ability for some causal reasoning, although I think some people like Gary Marcus would argue to the extent of that common reasoning. There's some basic common sense in GPT-3, and it can do basic arithmetic, even factorials and things like that. The difference here, the big kind of underlined bold thing that's going on between Alex the Gray Parrot and GPT-3 is that every time you want GPT-3 to do any one of these tasks, you have to retrain the entire model to do that task. Whereas with Alex the Gray Parrot, when you teach him to count, he does not forget how to fly, or he does not forget what he learned about basic language. So in Alex the Gray Parrot and humans in general, there's one brain which is absorbing this information and not degrading prior learning. But in AI models, every time you want to learn something new, you basically throw out everything you learned before. So it's difficult for me to see how we're going to get to some like general level of functioning or some if you don't like the term general intelligence, multiple functionality in AI models, because basically what they're very good at is narrow functionality. And so I don't see in a system that's resource greedy and that has this problem of degrading prior learning for the sake of current learning, how we're going to get to multiple functionality without making these things so large that they're only able to be run by the leaders in the field, which is also not what we want for beneficial and democratized AGI system. So I hope what I've done up to this point is kind of motivate why we should care about efficient AI systems. And it's multifactorial here, right? Like there's many things in here. You want carbon emissions to go down. You don't want you don't want these AI systems to be so expensive that we can't train them, or that only the leaders in the field can train them. We don't want to create these systems that are just so large that their only narrow functionality is switching between different models. If we really want AGI, we're after something more like Alex the Gray Parrot and not GPT-3. So there's a lot of motivation there. So kind of the question, it's a rhetorical question here. I'm not going to answer it for you guys, but kind of this emerging debate does more computation equals more intelligent or more intelligence, right? So personally, I'll answer this personally. I think no. I think there's a lot to unpack here, right? It's not just about the number of nodes you have, it's about how you're using those computations. And there's some arguments to be made on both the AI side and the biological side. But I think this is a big unanswered question. And I think the sooner we can answer this question, that will give us some insight on how we might want to be training these AI models. So I want to switch gears to talk about a solution, a possible solution. So I've been complaining about these AI models and how I don't think they're great. And there's another way to do these things. There's a solution for this problem of catastrophic forgetting and being able to learn efficiently. So the recommendation architecture is it's traditionally known as a framework for understanding higher cognition in terms of anatomy and physiology. And basically that just means it's a theory of how the brain works, right? And there's many different theories of how the brain works. There's global workspace theory, there's predictive processing, there's integrated information theory. These are kind of more theories of consciousness, but the underlying kind of cognitive processes that bring about this ability to learn generally or to attend to different things as you would in a sort of conscious system. These are kind of the four camps that we have. And I really like the recommendation architecture, which is proposed by Andrew Coward at the Australian National University, who helped on this paper, because it explains the problem that we're having in AI. It explains this concept of resource management. So resource management in the human brain is not like one particular area. It's not like just the hippocampus or just the cortex or some like fancy loop. What Andrew Coward has done here is he's taken as much neuroscience literature as one human could possibly read over the past 30 years, integrate that into one framework for understanding how the brain is working. So that's what this recommendation architecture does. And there's a ton of literature on this. And if you look it up, basically what Andrew's done is tried to provide an understanding for how the brain works. And so we can take that understanding and apply the same principles to our AI models. So we're not recreating the brain here. We're not saying that you have to have these same neuron dynamics, anything like that. We're just saying that there's some core foundational principles in the recommendation architecture, which I'll just call RA. So in the RA, that can solve this catastrophic forgetting and learning while degrading prior information problem that we have. So in RA, we have this thing called resource management, and it is controlled by basically three things. So synaptic pruning and growth allows for new connections, right? So our brains can create new synapses and break down synapses, and that helps us learn novelty. So this is all what the RA says, right? And the hippocampus manages to change the cortex without degrading existing learning. And it does that by essentially creating what we can understand as a record of simultaneous pass firing. So we'll come back to that in a minute. But essentially, this ability of the hippocampus to help manage change to the cortex without degrading existing learning helps retain stability while staying sustainable. So basically what that means is you're able to integrate more information without creating chaos in the system, and also without expending all of your resources, because in the human brain, you have a finite number of neurons, and every time you change a synapse, you better be careful that you don't accidentally short circuit the system, right? Which doesn't happen to us often. So kind of the third factor here of the resource management in RA is that these cortical patterns of activation can be part of multiple condition detections. So I know that's kind of a large statement, so let me unpack that. So by condition detections, we mean an analogous term in deep learning would be your feature detectors. So if you're learning information, whatever is storing that information and creating the kind of mapping of what that information means is a condition detection. You've detected a condition either internally or externally, right? And these cortical patterns in the brain are what set up these condition detections. And so when you have patterns of activation in the cortex, these patterns can be used for multiple things, right? And so this is kind of what we see in deep learning. If you look at lower level features, you see Gabor-like filters. Those Gabor-like filters are used to identify many different object categories in, say, like a classification task. So we kind of see that going on, but what we would like to see is a lot more of it in such a way that if you like completely dropped out part of the neural network, it would be able to recover and adapt in a similar way that the human brain does. So for kind of an important thing about resource management is that it expects that the system has some hierarchical organization. So in the brain, obviously that looks like cortical layers, right, with columns that help integrate information into groups. And then those integrations decide what information should propagate to the next layers. And that in part helps with stability. So I don't want to go into too much brain details. There's a lot of literature out here on this if you're super fascinated in this. Andrew Coward actually has a free online course that will take you maybe like 2 to 6 months to get through. It's super awesome. But the takeaway from this resource management system is the ability to learn efficiently in the RA. And so what we said was that the hippocampus has some way of managing new cortical expansions to receptive fields. So these little triangles are what we're calling receptive fields. And it's basically the ability to capture information, right? And so there's some management protocol that says, I know when I can make this receptive field capture new information or when it's full of capturing information. So that's one principle we can take away from the system. Another principle we can take away from the system is that the basal ganglia uses consequence feedback to interpret cortical condition definitions. And this is probably the most important point to understand about the RA model for the rest of what I'm going to be talking about today. So consequence feedback is something in the environment that affects the learning system in such a way that it actually informs the learning system how to redefine what it learned. So a very easy way to understand this is in reinforcement learning. So in reinforcement learning, you have a dog. It does something good, like you tell it to sit and the dog sits, so you give it a treat. So that treat is reinforcement learning, right? This is, everyone has probably heard of this, right? So that's an example of consequence feedback. You can also have teacher signals, like so when you have a little kid or something, and they're learning to count or they're learning their ABCs, and they say the wrong number or next letter in the alphabet, and you correct them and you tell them exactly what the correct output should have been, what the correct decision should have been. So all of these things are examples of consequence feedback. You have an agent, it takes in information, it makes a decision, that decision affects the environment, and the environment provides feedback, a consequence feedback back to the agent, which informs how its decision process was made. And so in the paper, kind of what we're also talking about is that consequence feedback can be conscious or non-conscious, right? So if you look at things like blind sight, there's a lot of other examples of effects where you may get sensory information and not be fully able to articulate that you receive that information, but it's still influencing the way you learn and how you modify your internal kind of thinking and brain setup to not do that in the future, right? So this idea of having consequence feedback to interpret cortical condition definitions is the biggest point. So now that we know what consequence feedback is, what we're arguing here, or the takeaway from the RA model, is that in the human brain, consequence feedback does not define conditions. It does not make the features. So in backpropagation, you are using consequence feedback in the form of an error. So you have some error between the actual output and what your predicted output is. And then you backpropagate, you send that error signal back through the entire network. And by doing that, you're giving consequence feedback to the initial features or condition definitions, right? We can think of those as kind of the same thing here, which is causing this catastrophic forgetting problem. So instead, what we're saying here is that you can still use backpropagation. You can still use any sort of consequence feedback like reinforcement learning, any of that stuff, but it should not be defining the conditions themselves, because when you do that, you run into this resource constraint problem, right? You quickly expend your resources because you're tuning these conditions specifically for whatever consequence feedback you got. And that's not what you want. You want condition definitions that can be used in a ton of different areas, maximally used across the different learning systems and tasks. Okay, so I hope that's clear. If it's not, we can come back to it. So another kind of feature that's going on for learning efficiently in RA is Hebbian learning and spike timing dependent plasticity. So this is something you see in a lot of machine learning models, like Boltzmann machines or spiking neural networks. So a lot of these principles are used in those kind of machine learning algorithms or networks, and it's very efficient. And so basically what you're saying is that things that fire together should be wired together, right? So things that occur together should have strong connections together. And the reason for that is because you're exploiting the natural structure of the world, right? You're saying things that occur together typically will continue to occur together. So stick those things together, right? And then we have this other thing going on, which is the cerebellum. So the cerebellum has more neurons than the rest of any other module in the brain, although they're much, much smaller. And essentially what the cerebellum is doing is just storing sequences of reoccurring behaviors. So if you've learned some pattern, like picking up a cup, that motion your hand is very familiar with, this is kind of where all sports come into when they talk about muscle memory. There is actual muscle memory, but there's also this sequence storing in the cerebellum. Okay, so these are some principles that we can take away from the RA model, is that there's some protocol in the brain. It's in the form of these like brain modules, but we can abstract that and think of it as some mathematical protocol that does these things. And so that's what we want to integrate into our AI systems. So if we compare this with what's going on in deep learning and reinforcement learning, which I'm just calling DL and RL here, is that most of our deep learning is driven by backpropagation. And in backpropagation, which is entirely consequence feedback driven, the error signal is used to update the entire neural network. So by default, or if you're not thinking about deep learning and you're thinking about reinforcement learning, you have a reward function, and that reward function is updating everything in the neural network or RL system. And when you're doing that, you're going to fine tune for whatever data is at hand, right? You're trying to get what is directly in front of you correct, and you don't care about what happened in the past. And if you make these models sufficiently large, by default, you can end up having some information about the past, which will help you in the immediate future, which is exactly what we're seeing in deep learning and RL. But in both cases, of deep learning and reinforcement learning, what we're seeing is that error and reward are used as a type of consequence feedback that updates the models and drives learning. And the result is that you need more resources to learn more information. Right, so that's what we're currently seeing, and that's not what we're seeing in, say, the RA model. So if we look at kind of this first diagram up here, which I've just labeled normal, so like normal AI stuff or machine learning, kind of the trend in the field is that you have some nodes which identify features. Those feed into decision nodes or some final output layer. And there's some consequence feedback, normally in the form of error or reward, that propagates that information back to the feature detectors, back to the feature nodes. And in the RA model, we're not getting rid of that loop, right? We still have the decision nodes and consequence feedback, but we're restricting consequence feedback's ability to affect the feature nodes. So there's a hard cutoff between this feature node system and the decision nodes, and what consequence feedback, whatever algorithm that is allowed to influence, right? So that's super important. And so now you got to figure out an alternative update or learning mechanism to learn these feature nodes. And so kind of like I was saying, the big takeaway here is that consequence feedback update algorithms or learning algorithms shouldn't update the feature nodes because it requires more resources, because you're just forcing these feature nodes to be tuned to this information. So I think I've beaten that concept down enough. Hopefully it's clear. So what we did is we implemented some of this stuff. We implemented a very low level version of the recommendation architecture in the coding language Smalltalk. That's a whole nother discussion of why it's in Smalltalk. But what I'm going to do is kind of share some early results with you from this experiment. So I want to draw your attention to this diagram on the right. because it's just super important that we understand that in traditional backpropagation and reinforcement learning, you have your model, it makes a behavior that affects the environment, consequence feedback affects all the layers in the neurons. In the RA model, which is kind of hard to see down here, there we go. You have your feature detectors, which is this layer of cortical neurons. And then you have your decision nodes, which is basically kind of a implementation of the basal ganglia, which has 3 or some number of output layers. So this is like your output layer and your feature detectors. These things integrate and make a behavior, which affects the environment. And then the consequence feedback only affects these decision output nodes, right? And so these layers of cortical neurons, the way they're implemented in the RA, are learned differently. So this is the same diagram. So now that we understand this consequence feedback thing, let's switch focus to the alternative update. So if you need to learn features and you're not using backpropagation, essentially what we're doing in this model and our model of recommendation architecture, there's different ways to do this, right? You could look at extreme learning machines, you could look at unsupervised and supervised mashup models. But what we've done here is we've set up a hierarchical series of integrate and fire. So each neuron is not just a node. Instead, each neuron is a collection of numbers which represent a synaptic or a dendritic branch. And so those synapses in the dendritic branch will first integrate and propagate to the rest of the neuron in the model. And then all of the dendritic branches will integrate and then propagate to the column population, right? So we have dendritic branches, we have we have synapses on a dendritic branch, we have dendritic branches, those integrate to one neuron, which will fire to a population of neurons in a column. And then we have different layers within columns that will integrate and fire and propagate information. So there's this hierarchical series of integrate and fire, which is important to be able to set up this alternative learning protocol. Another thing that's really important here is that we have a column bias on input groups that occur at the same time. So everything you're seeing in this slide right here is basically an algorithm that we've implemented in the RA model, which updates the feature detectors, which we end up just calling the cortex module. And so basically column bias just means that it's kind of a Hebbian learning protocol, right? That you're going to make things that occur in the past be wired together more strongly. You're going to increase those weights. And then the other kind of facet that's going on here is synaptic pruning and growth. So there's a sub algorithm that runs in this larger alternative update algorithm that will lay down provisional connections or weight changes. And then when the model is learning, it will either use those provisional connections and weight changes, or it won't. And if it doesn't, then we'll take away the changes and revert them. So that's our synaptic growth and pruning. So all of this is the alternative learning protocol that is used in conjunction with consequence feedback in the RA model. And so what we saw, let me back up real quick, because you're probably wondering, like, what is the task? So basically what we've done is we've set up a learning task in which no two inputs are ever the same, right? Because we were talking about how we want to learn novelty efficiently. So essentially what we have is a very simple task, right? There's very early results for this system. This system is put together, it needs a lot more expansive training, but we want to test it on something to kind of see our intuition on whether or not these principles in RA can be translated into a digital circuit. So what we did is we took basically a big array, 200 by 600. And if you have an array all filled with ones, and then you take a gamma frequency. So gamma frequency is just like a line, like a cosine or a sine. It's a wave function. So if you take a gamma frequency and you use that as like a cookie cutter stamp, and you cut out each row with that cookie cutter stamp with the gamma frequency, that will make our inputs. And in order to create categories, because this is a categorical task, right? We're trying to identify, is it category 1, 2, 3, up till 30. We slightly perturb the gamma frequency cookie cutter according to some random projection that is assigned to that category. So basically, there's going to be some natural structure to the gamma frequency, some like slight perturbance that is associated with a specific category. And so we make our inputs 200 by 600, sorry, 400 by 600 with these slight perturbations according to the categories, which essentially makes inputs which are never the same, but have some natural structure that is associated with one category over the other. So that's how we're getting these constantly novel inputs. And during training, we always generate a new input. So the same input is never seen twice. It's not seen twice in training. It's not seen twice in testing. If you ran this model like today versus tomorrow, all of the inputs would be completely different, right? The inputs are never the same. They're generated on the fly, but they do have structure. And so the goal is for the model to identify which category 1 through 30 the input is associated with or belongs to, right? And so what I did is we compared this RA model with ResNet and DeepQ network. So residual net or ResNet and DQN are both very popular kind of state-of-the-art neural networks. And so ResNet is a standard classification neural network. It's very good at classification tasks. It's still used for a lot of stuff today, although I think it's getting kind of replaced by maybe YOLO or some other emerging models. But ResNet is very good at learning classification tasks. DQN is a hybrid model of reinforcement learning and traditional neural networks. So the reason that I wanted to compare with both of these is that ResNet is completely error-driven, while DQN is both error and reward driven. And another thing that I'm not showing on this slide here is that we tried to get a complete reward driven model to learn. And so we chose eSARSA, expected SARSA. So it's a reinforcement learning protocol. It's not a neural network, and essentially only uses reward. The issue is that I could not get eSARSA to train because the complexity of the task was too hard for eSARSA. So there may be other reinforced or reward only learning models out there that can learn this task, but the ones I tried weren't able to. And so we're only focusing on error and then a combination of error and reward. And so what we see here on the left is the number of parameters times the number of learning iterations needed to train these models to either 75% accuracy or 90% accuracy. So what we did is we trained the models as far as we could, up to like, max till accuracy tapered off. And then we saved those models and then we ran them on a test set. And the test sets that got either 75 or 90% accuracy, that's when we cut off the training inference and said, okay, this is how many numbers of iterations and parameters you needed to learn to this % accuracy. So we see automatically that the DQN takes far many more, what I'm going to call computational steps. So there's more computational operations going on in these models than just the number of parameters times the number of learning iterations. But at the core of these models, this is the number of like learning update steps that is needed, or a close approximation to it. So I'm just going to call these computational steps. So the ResNet is a smaller model in terms of number of parameters. So, and it needs less learning iterations. So there's a difference in the billions of computational steps needed here. What we see, which is really promising and interesting in the RA model, is that to get to the same amount of accuracy on the same task, you need orders of magnitude less computational steps. So this graph is in billions, and this graph is in millions, in case no one caught that. So what we're seeing is orders of magnitude less computational steps needed just by separating out the condition, definition, learning phase from the consequence feedback. And so this is the same information, just in a different format. I'm showing you the difference between the number of computational steps the RA model needs versus ResNet and DQN. So compared to DQN, the RA model is like 475 times more efficient. Compared to the ResNet model, the RA model is about 95 times more efficient, which is what you saw up here on this slide. That holds true when you go from 75% accuracy to 90% accuracy. So you drop a little bit compared to ResNet, but still we're talking about many, many times difference in efficiency. So another thing that we are interested in is not just being able to learn novelty efficiently, but we want to be able to retain learning without degrading prior information. So one way that we can test that is we can learn a task, task A, learn another task, task B, and then return to task A, test on task A, and see how well we did, right? And so that's exactly the experimental setup that we ran here. And so I ran that with both RA, ResNet, and DQN model, right? And what you're seeing down here on the x-axis is a training mode. So if we're looking at normal, it's exactly what I just said, is that you learn task A, you learn task B, and then you test on both task A and B. And then we also did a control test which we're calling full, which is you learn task A, and then you learn task B, and then you learn task A and B together, and then you test on AB, right? So you're just, instead of like switching to testing, you're just relearning everything. And then there's one bar in the middle here, which we only ran for the recommendation architecture model, which is you learn task A, and then you learn task B. And then what you do is, instead of providing what the correct answer is, what the correct category is, you only tell the model whether it was correct or not. And so you would only be able to compare this learning mode with something that is fully reward driven, because both ResNet and DQN rely on backpropagation, and that backpropagation needs to know what the correct answer is in order to send any sort of feedback back. So that's why we had originally tried to test with the eSARSA model. So if anyone can get a reward-only learning protocol to learn this task, it would be good to run this correct incorrect task with that. And we've definitely wrapped that up into future work. We'll try to tease that out later. But kind of the takeaway here is, so we're looking at number of resources needed, right? Oh, I'm sorry. This is incorrect. We're not looking at resources needed. We're looking at % accuracy on the entire test set. So what we want to see is that if our assumptions about the RA model are correct, and that you can learn more efficiently and you can retain prior learning by changing the setup of these learning algorithms, we want to see that this pink bar, which represents the RA, is always higher than the rest of the bars. And that's what we see, because that means that the accuracy of returning to the prior task after learning something new is retained. And what we also see from this graph is that if you just do a simple pass, just one pass over the data, or a new set of data in this case, because the data is always new, and you provide incorrect or correct feedback instead of the actual category, like not an error, but just like a reinforcement learning protocol, you can recover some of the accuracy that was lost from the split training task. So this method is very effective because essentially you're only adding one more pass through the parameters. You're not doing a full training pass again, and you're able to recover some learning. And this control test here tells us that we haven't just relearned everything, that one training iteration was not enough to just relearn everything, because if it was, we would have saw this bar in normal and this bar in full would have been the same. So now that we've identified that the RA model can return to prior learning after learning something new more effectively than ResNet or the DQN model. And so another interesting thing to look at, sorry, there's a hamster in this room and it's making my nose itch. So if you see me niching my nose, it's because I'm allergic to this hamster. Sorry. Okay. So yeah, so we're just going to look at the RA model. And so there's a lot going on here. So let me kind of unpack this. So what we're seeing is that in the RA model, you have your first guess of what is correct. So if you're familiar with a neural network, you have an output layer, and that output layer has like 30 nodes in it. And you normally take the max value of those 30 nodes, and that's what tells you what your prediction is. And so if you take away that max, and then you take the next max of the remaining 29 nodes, that would be your second prediction, right? And then you could get a third prediction and so on, right? So you could rank how confident you think each category is for the given input information. So that's what we're calling first, second, and third. So when we're learning, we're using the first guess, the first prediction output, to identify our accuracy. So that's what you saw in all the other graphs. We're looking at first accuracy choice. What we're looking at now is the comparison between first, second, and third choices. So here again, we have usual, which I called normal in the previous slide, correct, incorrect, and then relearn, which I called fool. All right, so same different training modes here, but we're just comparing how correct is the first from the second and third. And we see that what we want to see here is that the blue bar, the first prediction, is always higher considerably from the rest, because that gives you a measure of confidence. So you're saying that the RA model is quite confident that this category is correct over any other category. And then what we want to see is that the second category has a high accuracy. And so that's what like the idea that the second category is almost always right is what allows us to implement this correct and correct feedback mechanism. Because we can just say, okay, the first guess isn't correct, default to the second, right? And so because the recommendation architecture has kind of tiered the output and learned, okay, I think it's most likely this, but if it's not that, then it's going to be that, right? That sort of internal setup in this RA model allows it to do this kind of one-pass learning, this one-pass learning shot in the correct and correct feedback. And the more important graph that we're looking at over here on the right is the ratio of the first to second category batches per choice. And so what that basically means is that when we learn task A, which is the first batch, versus the second batch, which is task B, we want to see that the number of, in the test set, the number of correct category identifications that we get in the first batch in task A is proportional to task B, because that means that we learned things efficiently, is that we're saving information efficiently. We're not just learning what we learned second. We're not just retaining what we learned second over what we learned first in task B versus A. And so if that's true, if we have an even retention of knowledge, we would expect that these bars are as close as possible to 1. So in this first task, what you're seeing, or at this first bar, the first prediction guess, is that there is a bias on the second task, right? So you learn the first 15 categories, then you learn the second 15 categories. There's a bias on the second 15 categories, but it's not so strong that it is making up for the entire accuracy in the test, right? In the evaluation metrics, right? So what we see is that some knowledge in task A was preserved. Interestingly here, we see that the second and third guesses have a bias towards the first task. So knowledge is being retained, but there is a slight pressure on this most recent knowledge. If you use this correct and correct pass, you even out these bars considerably. So this correct incorrect single pass learning trick is very effective for helping retain information, because you're basically promoting a redistribution of these ratios so that these third and second guesses get more skewed towards past information and push that information to the first guess, if that makes sense. I know it's a little complicated, but basically we're just showing that you are retaining information from the first task, and that if you use this correct incorrect pass, you can recover a balance between the bias of information learned after information learned prior. And what we see that is also really quite strange here is that if you just relearn everything, right? So you learn task A, then you learn task B, and then you learn both task A and B together all at once in a full training episode, not just one pass, that you end up being more skewed towards the first information. I'm not sure why that is. It could not be significant, right? It could just be by chance here. It could not be significant. But kind of the idea is that this retention and knowledge is not the same as relearning everything, which is our control, right? Okay, so that's basically it. I'm sure there's a lot of questions. I just want to give thanks to Andrew Coward, who did a lot of amazing work on getting this recommendation architecture into it. And then my postdoc advisor, Susan Schneider, who helped on the consciousness stuff, which we didn't really talk about, but you'll see it in the paper. So I'm sure there's lots of questions. I'm going to leave my slides up unless we move towards a more discussion format.
Well, thanks. That was great. So any questions? If we use the raise hand feature, that puts you at the front of the line if you want to go that way. Anybody? So we got
I am curious why you small talk.
Yeah, great question. So the work that Andrew Coward was doing was he started this work back in the 30 years ago. And he used to work for Nortel Networks, which is an offshoot of Bell Labs. And so around the time that he was coming into like and he's been working on these ideas since like 1995, right? Maybe even earlier. So he's had some small implementations of kind of these ideas over the past 30 years. And around that time, when he was making the early instantiations of these implementations, Alan Kay came up with small talk. So I think that there's several like functional reasons. Probably the reason that it's still in small talk today is a time reason. We're in the process of porting this model over to Python and PyTorch, so it's more easily comparable with current state-of-the-art AI methods. One of the kind of limitations here is that we can't directly compare time or memory. So if you end up reading the paper, one thing I did was take like the amount of megabytes needed to store these models in computational memory, whether it be like GPU video RAM or Smalltalk RAM, virtual memory RAM. And those comparisons aren't really reliable because we're using different language and different environments. So yeah, we'll definitely be porting that over. The advantage of Smalltalk is that since everything is object oriented, your ability to pass electrical signals and do this like hierarchical integrating of information becomes a lot easier, because you're just sending messages to things and everything's an object, so you can send a message to anything, right? Which I mean, you can still implement in a different language like Python. It's just a lot easier in Smalltalk. And then if you want to make a change in Smalltalk, it's very simple, right? Because you're just changing an object or you're changing a message passing protocol instead of like an entire function or class. Does that make sense?
Yeah.
I think we've got a question from Michael. Michael here.
Hello. So I had two questions. One was about a slide that was way back there. I think at this point I may even have forgotten what the question was. I think it was yeah, a few ahead with the models of, sorry, not backwards. I mean, it's like around slide 9 or 10, I think.
This one? This one?
maybe like 12 or 13. Yeah, is it? No, back one. There we go. That's it. Yeah, that one right there. Is it normal practice to use the stick figure for environment? Because that sort of makes me feel like it's referring to like an agent instead of the environment.
Yeah, so no, I don't know what normal practice is. I don't think people typically draw out these diagrams at all. I think it's kind of assumed that there is this like cyclical loop between the agent and the environment, where information is coming in from the environment and then getting propagated out to the environment and then coming back into the environment. All I'm trying to show here is that the consequence feedback coming from the environment, which is, you know, either internal or external to the agent. Well, the consequence feedback is always external and you know, in biological models, but in some AI models, it is also internal. Is that it's not affecting all of the layers, right? It's only like in AI, it's affecting all the layers, but in the RA model, it's only affecting our basal ganglia module and not our cortical module. And the cortical module is what is defining the features, and the basal ganglia is what is deciding what decision should be made based on the cortical features. So like another way to think about this, it's kind of like a silly analogy, but it works for me, is that if you think of the feature definition module or the cortical module, what it's basically doing is like painting an abstract painting, right? And then the basal ganglia or whatever decision module comes in, looks at that abstract painting and tries to interpret what that means and what decision should be made. And then consequence feedback. So if you imagine in this painting example, someone walks up to a piece of abstract art and goes, oh, I think this artist was angry, right? And then the artist just happens to be standing nearby, and the artist says, oh no, I'm actually showing like the beauties of war or something. I don't know, I'm just making this up, right? But this example holds true because now that consequence feedback is only going to inform the person who's interpreting this abstract painting. It's not changing the actual painting, the actual patterns of activation themselves. It's changing the interpretation of the patterns of abstract or the patterns of activation.
Okay, so it's not in any way implying that there's another agent in the environment.
There can be, right? There for sure can be. I mean, so in the case of consequent feedback with a teacher signal, there is absolutely another agent, right? Which is giving you, no, this is correct, right? That's incorrect. This is what the correct thing is. There doesn't always have to be another agent, right? It could just be that you put your hand on a hot stove and it hurts. And then you have neurons which send that feedback to your brain that says, we don't like that. Does that make sense?
Yes. All right.
Rachel, is the paper complete, and can we have a link to it?
It's not complete yet. So I mean, it's under review right now. So after I get some initial feedback, I will wrap it up and put it on Archive, and then I'd be happy to send it out. I'm just waiting for like some editorial comments before I do that.
Okay.
But I'm happy to share these slides if anyone wants the slides.
I think Howard has his hand up. Howard?
Yep, I'm there. Let me lower my hand. Great talk. It was my first time here, or second time here at the group. It was a great talk, nice presentation. I like the RA model and everything you presented. That was clear. I was just going to say though, a lot of this stuff, well, two things. One, but everybody does it, like AI is equated to deep learning, but I'm not going to comment about it. That's just part of the world. I'm actually in Toronto where, deep learning is a religion here. Good luck saying anything to do with symbolic stuff. So I'm okay, but I'm just saying all the time people keep saying, in AI, this happens, in AI happens. Not in my AI, but I know in everybody else's AI, this is what happens, but just saying that. But my other concerns is, I think a lot of the comparisons to the brain or to biological systems aren't correct. Just pointing it out that, even like, for example, you gave on that slide that you just, well, first of all, small talk is okay. Small Talk, I think, was on the cover of, I'm older than Byte magazine. I think it was 1981, 1982. It was on the cover of Byte magazine, 1982. So just to date the software. But that was sort of cute, the Small Talk. But the other stuff with biological systems, you know, parrots are not a good comparison. They're not mammals. They don't have a cortex. I wouldn't use it as comparison. 1, 2, parrots, they can't do causality. On PBS TV shows, they do causality. But in real life, it's really associative behavior. Chimpanzees cannot do causality. If you have a tube and you give them a stick and they're able to push the food out with a stick, but if you put a gravity trap, it takes them 160 tries because they don't understand the cause and effect of gravity. Humans, on the other hand, even somebody who's impaired, they can do it then because we can do causal behavior. They can't. Just something very important in terms of causality. Parrots can't do causality, and GPT-3 cannot do causality. So I'm just saying that comparison. I know it seems like a trivial thing, but it's a huge effect for the work I do. It can't do causality.
Yeah, I think it depends on who you ask, which is kind of what I stated here. Like for you and Gary Marcus, for sure, GPT-3 is not doing causality. I would tend
Parrots
to
can't
agree
do
with you.
causality either.
Yeah, well, again, I think it depends on like which researcher you ask. I think the bigger takeaway that I'm trying to show here is that we're not getting generality out of our AI or our deep learning systems, right? And I'm also not saying generality out of like some of the symbolic architectures within resource constraints. So there is generality in symbolic architectures. They're much better at generality. But there's still this question of resources and how do you put more information in there? I feel like encoding all of any language like English language or something is sufficient enough to have a symbolic architecture which is as generally intelligent as we want it to be. So yeah, I appreciate your comments on definitely pointing out that not all AI is deep learning. You're definitely correct there.
But the other things too, but everything with the brain, like recovery from damage. So, you know, you can have the brain massively impaired, not because something's missing. There could be somebody has an accident, swelling around the midbrain. They get decadron, they get swelling goes down, memory comes back. There's other reasons too. I'm just saying a lot of the examples are not correct, whatever.
So do you think that when the brain is like, you think damaging a brain degrades information more than it does damaging like a neural network?
Depends where in the brain. Brains are not, well, by neural network, you're assuming deep learning. Deep learning means, you know, the religion where it's just, you know, these massively interconnected networks. No, the deep learning thing is probably more robust because the brain, if you hit certain parts, you're going to have big problems, but other parts, it won't matter. You know, remove part of the frontal cortex in somebody, the other frontal cortex is there. Things won't be so bad. But, you know, you hit another part, you're going to have big problems. It's because just like with the parrot, just the brain is not a neural network. It's not deep learning at all. It's, you know, there's different things that do different things. That's what I'm saying in terms of the analogies.
Yeah, no, that's I'm agreeing with you. That's my whole point, is that the brain is not deep learning and it shouldn't be treated like deep learning, and that
but even in the model where you say like the hippocampus ensures that, you know, keeps memory alive or whatever. Actually, that's not true. It's really hard to remove memories in people. People have bad examples. Good luck removing the memories. You know, if you remove, years ago in Montreal, they took out hippocampi of people for seizure surgery. And what happens is, even without the hippocampus, the old memories are there. The old memories, you can remember things perfectly. They can remember what they did in grade 2 or something. So the old memories are without the hippocampus. I'm just saying the biological, in terms of lifetime learning, I'm not an expert on it, but I know there's all these schemes to keep things going. And the RA model you gave was good, but I'm just saying the biological comparisons is, I don't know, I'm just saying a lot of it doesn't reflect reality in terms of, you know, of humans, chimpanzees, parrots.
Howard, I think you made your point. Why don't we move to the next?
Sorry, but anyways, sorry about that.
Yeah, thanks, Howard.
No problem.
We've got a lot of questions coming up. So how about Boris? I see your hands up.
You need to unmute Boris. So
Hi, sorry, I was a bit offline. Thanks. So I have two questions. You have these decision nodes that to me look like experts in a mixture of experts architecture. I mean, they also have, you can think of it as a cortical column or something, or you're thinking about it as a part of striatum. But you can make many different cortical brain analogies to it. But the idea is you have areas that are experts in some behavior or recognition or sensory area. And you basically, if you match those areas with an input or a consequence, whatever, you train those areas and you leave others alone. Does it make sense? I mean, theoretically, it's
Yeah, we're okay. So there's kind of two things I want to clarify there. One is that we are not at all trying to implement the brain, right? We're kind of using some lazy language to explain how this model is set up. What we've done is taken some interesting principles that theoretically inform how to solve a problem and use those principles to create like a mathematical analogy to help solve that problem. So yes, I mean, there's a million different interpretations of the brain and how it works. So this
right. I'm sorry, I didn't want to get
Yeah.
into that. I mean, there is an existing field in deep learning. It's called mixture of experts. And
Okay.
they're doing precisely what you're describing as far as I can tell.
Yeah, that's my second clarification point. So this decision output are not analogous to experts and like what you're talking about. I mean, it may be similar. It may be really similar. I'll certainly look into it afterwards more to see how similar it is. But essentially, if we go back to kind of the artist painting, there's a collection of single nodes or neurons in this decision group, which we're just calling the basal ganglia module. And it's looking at the cortical module, and it's getting, you know, some layer 3 outputs here. And it's basically trying to recommend a behavior. So these errors right here are recommending a behavior that the agent wants to decide. So which category is it happens here. But there's groups of these basal ganglia kind of neurons, like cortical groups for each category output. And so I think the more closer, like the closest thing to this that I've seen, and it might be the case that your mixture expert systems are similar to, is like an extreme learning machine. So in an extreme learning machine, you have like a matrices of weights and you just propagate through them randomly. And then you have an output layer and you only learn the connections between like the final weights in the output layer, right? You don't learn all the stuff in the box in between. So it could be the case. I haven't really looked a lot at the mixture expert systems. But the idea is that these neurons are not tied specifically to the category, that they can be multiplexed themselves for multiple tasks.
Yeah, the experts can be motor or sensory, as far as I can tell. So the task would be the motor part, but or they could be mixed. You know, the motor part specific to some kind of sensory area. But the idea is, I don't think there are any clear distinctions, but you're talking about selective learning, where you first have to match the category. You can call them a decision area, or whatever neuron is associated that you call basal ganglia, which doesn't really have to be basal ganglia as far as I can tell. It could be just cortical area that is an expert. Like cortical column is an expert in some specific either behavior, if it's motor, or specific type of input, if it is sensory. So that more coarse association where you kind of you have a hierarchical approach, doesn't have to be two layers, you know, the input and the decision. It's actually a hierarchy where each high level is more coarse, is aggregating several modules from lower level, and you do this backpropagation and reinforcement learning, both of them actually. It's usually a combination of the two that goes down, and then the learning becomes selective to that higher area. That is, you don't train the whole model. You train. You have this top-down path where let's say you have several nodes on the top level. Each node propagates down.
Sorry to interrupt, Mike. How long do we have for this? Because I think we're kind of over
Yeah,
time.
I was just gonna,
Let's
I
go
was
on.
just
We
gonna
can wrap
wrap
that
it
up a little bit.
A lot of time.
I hate cutting
It's
people
a great
off.
question, Boris. Thank you for that. But I think
Yeah,
maybe we have to move on.
Boris, do you mind if we move on to Monica's had her hand up for a while?
Well, means
Thanks a lot, Boris. Thank you.
So, can you provide a justification for the idea that catastrophic forgetting is bad?
Yeah. I think it's bad because it relates to the idea of, I think it's bad in the sense that if you want a multifunctional system, if you want narrow learning, catastrophic is totally fine, right? If you want a more general functionality or the ability to learn out of domain and retain prior domain information, then I think catastrophic forgetting is bad. And that relates to this capacity to compute. And so I think catastrophic forgetting is bad if you're saying that deep learning is going to end up being generally intelligent, which some people are still saying, right? Because we need to make these models larger and larger, and we don't have the ability to continuously make them larger and larger forever. And so if we could learn new things without catastrophically forgetting what we previously learned, that would extend our ability of these systems to be more general.
Have you considered using Darwinistic systems, because they basically discard the losers, and they basically learn better over time by creating better abstractions, and the good abstractions cause the prior less effective classifiers to be discarded as inferior. So that kind of systems are resource manage themselves. And I find those to be a very interesting way for resource management. Thank you.
What was the name of the system? I kind of missed what you said there. Sorry.
Darwinistic systems.
Darwinistic. Okay.
Yeah, evolutionary computation in general, basically.
Yeah.
There are I work with evolutionary deep neural networks.
So genetic algorithms, that sort of thing. Gotcha.
Yeah.
Yeah, that's actually what I did my dissertation on, was evolutionary DQNs, and they have very similar properties to the results I'm showing here. But yeah, it'd be interesting to do a comparison between like an evolutionary DQN and the RA model in terms. Yeah, cool. Thanks for bringing that back up. I'll look into that.
So, Hugo, I think you're up next, aren't you? Or
No,
I'm not
I
sure who.
believe Lance is next, and then it's me, and then it's Stefan, based on what I said.
Okay.
Yeah.
Oh, yeah. So I thought it was a great talk. It was very clear. I guess one thing I would love to know more about the RA algorithm. I get you mentioned that course. I'll look into that. One thing it reminded me of a little bit is Jeff Hockman's hierarchical temporal memory. I don't know if you have looked into that at all. I know that uses a lot of memory. So yours sounds very promising in that if it actually solves catastrophic learning, that would be amazing, and I hope it does. But I'm wondering what issues there are. Like, does it take a lot of memory? Is it slow? Can it be used in production?
Yeah, no, these are all fantastic questions, and thank you. Yeah, I really like Jeff Hawkins' work. I'm really partial to hypervectors and kind of some of the stuff. We're making a hypervector processing chip at Simuli. So I'm hoping Jeff Hawkins will use the chip one day. So I'm really partial to his setup. That's not what's going on in the RA model currently. There's not enough testing. I mean, this is just first results, right? There's not enough testing for me to tell you kind of the core limitations of this system. It's quite an actually very large system, and it's just the base. It needs to be scaled up, right? So I don't have enough experimental data to really answer your questions of like, how much catastrophic forgetting does this solve? Is it the actual solution? Like, what are the pain points in using this system? That's all stuff that we're racing to answer because we would like to use it in production. But like I said, the task was on some trivial probabilistic category identification. So until we can scale up the model and scale up the task, it's not safe to assume any of those questions, right? So.
And is there any fundamental blockers in scaling it?
No, I don't think so. Yeah, we want to get it out of Smalltalk to help us scale because it takes several days to run on Smalltalk. Part of the reason for that is that the virtual machine memory that's built into Smalltalk is small, and the system that it's being run on is also a small computer in terms of like compute size. So if we can port it over to something like PyTorch, then we can start to scale it up very quickly because we'll have the advent of like a GPU to help like run scaling tests quickly. But fundamentally in the actual architecture, actually there's some early preliminary results which are in the appendix of this paper that's coming out. The more cortical columns that we input, the more accurate the system gets. I'm sure there's a threshold. I'm sure there's like a sweet spot there, right, with everything. So
Last quick question: are you going to outsource the PyTorch code?
Open source it?
Open source, yeah.
Yes. Yeah,
Okay.
absolutely.
That's
Yeah,
nice.
I'm not making any promises on when that will happen though. It's quite a large undertaking to write this thing. It's a bunch of legacy codes.
Mhm.
I think Stefan
No,
Burpee.
it's Hugo's next.
You go, okay.
Hey, everybody. Rachel, great talk. Obviously a big fan of the work and looking forward to collaborating with you on all this. I just wanted to say that regarding the large language models, catastrophic forgetting, I've been personally working a lot with like, GPT-3, Da Vinci model, and also my, models I could run here, in my own home with like the NeoX with 20 billion parameters. And as I got into it, I realized they actually are learning some things that are resembling causality to a limited extent. And when I double clicked on that, if you look at the work at Tim Detmer's on large language model emergence, it turns out that what's happening is when you get above around 7 billion parameters, these models are actually learning how to intelligently forget. So they have a separate channel now that begins to kind of take context into consideration. And so in essence, it's learning what not to consider for a particular context. And so it's an automatic thing that's happening. And you can actually see it in the weights. About 5% of the large language model weights, when you get to the giant ones, are these high dynamic range weights, which you have to leave them as high dynamic range. And the beauty of that means that the other 95%, you can compress them down to 8 bits from 32 bits with no loss of any data whatsoever. But just wanted to say that while I'm totally on with you and with Gary Marcus on the skepticism, there is something else happening here. I think it's really important for us to engineer that rather than have 2 trillion parameter models, which are going to be way too expensive. But it's happening now, especially you look at that large language model emergence. It's just something to, I think it might be worth looking into.
No, for sure. That's a super good point, Hugo. I think that's kind of like the idea is that backpropagation is good. Like what we have is good. It's not bad, but we're missing something. And that's kind of the biggest claim here is that we're missing something. It is doing something. It is able to figure out what it should learn, right? What it shouldn't learn. There's properties in there that we like, but there's not all the properties that we need. I think.
And like with the backpropagation example, right, is that if you get to these enormous 175 or even above, say 10 billion parameters, and it begins to automatically partition the model and say, okay, in this case, I'm only going to consider a subset. And so in essence, you're no longer doing catastrophic forgetting for the large language models, as you can see with the one-shot learning, is not really possible even, right? Because they have channels that don't allow it to consider everything at one time. The backpropagation on a 10 billion parameter model is not across the model. The weights themselves are preventing that from occurring. But so the question, I think that what you're doing and what I'm also working on is engineering that, right? You shouldn't have engineering it, because probably you can do this this algorithm that's a more intelligent partitioned contextual backpropagation or whatever the learning algorithm is, even without backpropagation. You can engineer it so maybe it happens at 100 million parameters or 1 billion parameters, not 5 trillion, right? So very important direction, because the energy constraints that you mentioned as well are crucial. But anyways, thank you. That was very, very interesting talk.
Yeah, thanks, Hugo.
Okay. Yeah, that's very interesting. Stefan?
Yeah, hi all. I have 3 quick questions. The first thing is about Smalltalk. I've been working with Smalltalk somewhere in the previous millennium, somewhere in the 80s. So when I heard that name, I already knew that somebody has been working on it who's a bit older than the faces I see here for the moment. And it's also rather odd that this idea has not surfaced earlier, if it's already that old. But what I was wondering about, that one of the things which is great in Smalltalk is persistency. So in Smalltalk, you don't have to worry about memory structures, how to serialize them to disk, to file, and back into memory. So these are stuffs when I went away from Smalltalk, I had a lot of time to invest in it to get it back to work at the same level using memory mapped files in C++. And the question is basically, is that not going to be a problem if you now move away from Smalltalk, which you need to be, because it's an old language which is an environment that nobody's using anymore. But is that not going to be very time consuming to write all this code that is basically boilerplate code and not related to the functionality, but just doing input output?
Yeah, it's gonna suck. You're absolutely right. It's a massive undertaking, and it's not going to be fun. If you'd like to help on that project, we'd be more than happy to have some help, because it's a huge undertaking. It's a necessary one. I mean, I too love Smalltalk. I think it's a beautiful language. I wish it was upkept and kind of better or improved upon over time, but it's kind of lost a lot of support. So if we want these like kind of alternative methods to be used in practice in wide scale, we have to update them to the widespread tools. So yeah, it's going to be a bit of a challenge. I think the way that the model is written in such a way that it actually doesn't take up that much memory. It's only like 300 megabytes of memory. I have the paper right here. Let me double check those numbers before I just start saying stuff. But yeah, I don't see any reason we won't be able to do it. It is going to be a massive undertaking. Yeah, so it's 320 by 20 megabytes of RAM, which compared to DQN is like 3,000, or the ResNet, which is 2,000, around there. So I think we'll be okay just from how nicely the algorithms were written. But yeah.
Okay.
I think we're just about out of time, but how about, is there Mike Sorn? Maybe a quick question and then
yeah, quick question, which maybe I don't totally expect an answer to, but question about philosophy. This is very similar to what happens in an optimization of an objective function, and you're using training to optimize the weights. Now, if the weights are scalars or a linear function, you're subject to global minimums, and this forgetting is kind of a global minimum problem. Does GP3 or the technique you're using allow presenting the weights as an arbitrary function or some function to be trained on, or a table lookup, or some way that might solve this problem? Or is that how you're solving the problem, by manipulating the weights of the neural net in a particular way? I assume the neural nets are linear elements. Is that correct?
It's not entirely correct. So there's multiple learning algorithms. So we're using the traditional kind of reinforcement learning. It's not really a reinforcement learning algorithm because we're not quite using the Bellman equation. We're using more of like a spiking neural network protocol. So there's a protocol that uses consequence feedback, a learning algorithm. And there's also a protocol that is using kind of this Hebbian spike timing dependent plasticity learning protocol, which has all the things you see on the screen here in that algorithm. I can't answer the question for you on like if we can just do linear function approximation. I think that probably because it's math, yes. I don't know if it would be the most optimal way. I'd have to really think about that question a little bit more, but it's a great question.
How is the slides going to be distributed, and eventually the paper?
Can you send me the slides, Rachel, and I can post them?
Yeah, I'll send everything to Mike and then he can distribute it through his
The meetup. Yeah, it'll be
The
so it'll be
meetup
on
website. Okay.
The meetup site. So
Okay.
why don't we,
Thank you.
yeah, thanks, Mike. Why don't we wrap things up then? I think we scheduled for an hour and a half. And thanks a lot, Rachel. That was really interesting. It's not, there's some really exciting work going on now. It reminds me a little bit of Alexander Orobio's work, a little bit. I mean, it's kind of a non, traditional
Yeah.
deep learning. So anyway, and so I'll post the video, and I'm going to rewatch it myself. Next month we've got an IP lawyer, so come back with your questions. And with that, I guess we'll wrap it up unless anybody has any final comments.
Thanks a lot, Mike. Thank you, Rachel. Fantastic
You're welcome.
session. Appreciate it.
Yeah.
Thanks
Rachel,
so much.
Rachel, quickly, can you tell us how you ended up in a room with a hamster if you're allergic to hamsters?
Yeah, my friend's daughter has a hamster, and this is the quietest room, I suppose. I guess the hamster doesn't get that much attention. So if you didn't want to hear a little 4-year-old screaming, then it was the hamster room. So, yeah.
Okay, gotcha. Awesome.
Yeah, thanks everyone so much. Feel free to reach out if you have any further questions or comments. And thanks, Mike, so much for setting this up.
Oh, it's my pleasure.
Awesome.
Okay,
Take care,
bye.
everyone.
Thanks a lot. It was great.